So the last talk before lunch, we returned back to a MIT faculty member and a colleague of Ed's, Professor Bob Cohen. Bob is the St. Laurent Professor of Chemical Engineering. Bob is also recent fellow of the Materials Research Society and elected to the National Academy of Engineering. And with that, I'll let you go on.
Thanks, Klaus. I'm really happy to be here. In this next hour and a half, I'm going to tell you about some... I see people looking very hungry, and except for Ed, a few people are even looking tired. I see glances at the watch up there. But let me get some things out first that I would have left to the end. But obviously, I want to say thank you and congratulations to Ed. I owe everything to Ed. When I got my PhD from Caltech in 1972, chemical engineering was in a phase, in a funk, I think, but in a phase where math, physics, process engineering, process control, mathematical modeling of everything, continuum thought was prevailing. And a guy like me coming out of Caltech who had synthesized polymers and did structure property work was not very marketable. And I wanted to teach at a university, and I use that word advisedly. I'll come back to that. And MIT welcomed me, and it welcomed me because Ed was here feathering the nest and had been doing so for a long time. Molecular thought, the chemical side of chemical engineering, product engineering, however you want to say it. Ed was doing all those things when it was totally unpopular, paved the way for me to come in here, and I've enjoyed the 37 years I've been here, and I thank you for that, Ed. And I use the word teach. If you ask me what I do, I say I teach at MIT. I've heard Ed say that many, many times. And in the time I've been here, people may find this upsetting or unusual. Ed and I never wrote a single research paper together. There was a lot of territory, plenty of students, plenty of interest, lots of things to do. But we had a very strong common interest in this phenomenon, that is teaching, education, curriculum. And back in the 70s, I'll get to the date of this in a little while, Ed and I wrote a paper. Are our names on there? Yeah, there they are. It was published in Chemical Engineering Education about what we were doing in this department. And actually, Ed, I have a copy of that paper, which I'll give to you. The paper itself is still in perfect condition. We have to do a little thinking about what they had in that wonderful reprint paper to keep it so well preserved. Acid-free, I guess it was. In any case, we talk about things from the department, famous people from the department, and so on. The date is easily... yeah, right. Talk about jokes on oneself. That's obviously Ed. Who is that? But I put this part of it up because it's cut off here. It's 1976. And certain things I just want to point out that were in our curriculum. Obviously this, physical chemistry of polymers. But this object here, Polymer Science Lab, is something that Ed helped me with, encouraged me to develop. And it's been taught since 1976 to this day. And Ed and I taught it together once. I think even after your partial retirement, we came back and taught that class together, which was a great joy for me. This is another place where Ed and I have a very strong fellowship. We both taught out of this legendary book. Some of you have talked about the class. Ed and I have pored over this book, trying to understand it at all the different levels of thought. It was terrifying for me to think I'm going to follow Ed Merrill in the teaching of this material. And so all pride went away, I threw caution to the wind. I went into his office and said, I'm assigned to 1068, it still was then. Ed, I have to ask you, will you give me your lecture notes? He said, sure, no problem, if I can find them. He went, rummaged around in a drawer, and he pulled them out, and he said, here they are. 7 pieces of paper for an entire semester. That's all there was. And I think you now understand why. The whole Socratic, I mean, he had it all going. He didn't need notes. Anyway, I looked at those notes. The first page had all sorts of very important things about Florey's book. The first line of those notes was the following: "Why is a raven like a writing desk?" Does anybody know? Nobody in the world knows the answer. This is from Lewis Carroll's Alice in Wonderland, of course. And that supposedly that's a riddle that has no answer. The next line is something about, "I've seen many a cat without a smile, but hardly ever a smile without the cat." And that, of course, is the deuterium labeling of polymers where the Cheshire cat smile comes out in neutron scattering experiments. And you made that. That may be your most highly cited piece of work, actually, that comment. From those 7 pages, and actually the most important thing was numerology. It went something like this: 10, 12, 11, 13, and there's a 13A and so on. That's the sequence Ed taught me in the way to teach out of Florey's text, the chapter numbers. Start with chapter 10, then go to chapter 12. I would have never known, but Ed taught me that, and the rest is history. This book is not about Ed, but this allows me to sequence into the little technical part of my talk. The last man who knew it, maybe there will be a book written about Ed in this context, but the last man who knew everything according to this author was Thomas Young. Thomas Young, you guys have all heard of Young, Young's modulus, contact angle, which I'm going to invoke here. If you read this book, you find out he also deciphered the Rosetta Stone, practiced medicine, knew some things about light in terms of the particle-wave duality and so on. A guy just like Ed. He didn't go to Roxbury Latin. Somehow he managed to learn all these things without having gone there, Harvard and so on. He managed to go to Cambridge after a few years. But it's this part of you. Oh, by the way, Ed, this reminds me of those globes that we banged around in the basement of Harvard, Jamie Sykes Mercator globes. So let me just spend a little time talking about some work we're doing on molecules that should be of interest. My selfish reason for showing these slides is that we don't have an answer for a lot of the issues in our work, and maybe, Ed, you'll do some thinking about it. But they relate to silicone-like or SiO-containing molecules and their wetting behavior. And so as just an introduction, when a liquid is put on a smooth solid, what happens is that the interfacial energy and the solid surface energy fight with each other, and the interfacial energy is augmented by the cosine component of the liquid surface tension. And when all those balance out, you get this contact angle, and it's described by this very simple relationship that Young did put together a couple hundred years ago. So I will make use of that, and the details, I think, of what I'm going to say are not important, but just to remind us that if something is of a very high surface energy, like clean glass, water will spread on that because this vector gets large, and as the surface energy of the solid decreases, like water on Teflon, the contact angle becomes larger, the liquid wants to ball up. And there are lots of examples of these superhydrophobic surfaces. You need to invoke a certain amount of roughness. I'll talk to you about a certain kind of roughness that we've used. But the question is whether we could develop surfaces that would be wet, or not wet rather, by all kinds of liquids, including organics, octane, gasoline, pentane, things like that. The answer is we've succeeded, and we've succeeded in part because of the surface analysis, the topography, and also because of these molecules that will be the subject of what I'm going to talk about briefly here. So here's the kind of superhydrophobicity that you can get on the kind of rough surfaces modified with the right kind of molecules. Water, of course, is a high surface energy liquid, 72 millinewtons per meter. And there you see water struggling mightily and succeeding in holding itself together because of the surface tension. And the reason that it bounces along, and you'll see the coefficient of restitution gets larger and larger. This is a very elastic object after all the sloshing around finishes. But it's the topography and the chemistry of this surface that allow us to do that. This is like they say, don't try this at home. No one's ever done this before. The same kind of surface I showed you before. Now, this is about a factor of 3 lower in surface tension. You can see that. The drop is sagging under gravity here. So it's not as beach ball-like as the previous drop. And the question is, I'll let you vote whether or not the title of this movie is correct. Does hexadecane bounce? This is, and I'll tell you about the surfaces that allow us to do this. There you see it trying. Did it bounce? Oh, okay, good. I think it bounced. So, some things about these surfaces. First of all, they have to have the right topography, the right texture, the right roughness. And that roughness is a roughness that bends back on itself. We call it reentrant curvature. These are reentrant structures. They're kind of cut off here. This sort of fits in with the Mad Hatter Queen of Hearts theme of your teaching. Cylinders or fibrous textures work. These nail-like structures, that's the kind of surface that the water and the hexadecane were bouncing on. There are some examples in nature, many examples in nature, the lotus leaf. But the point is that you have to have a back reentrant kind of texture so that the native contact angle of the liquid on this red solid is always bigger than the texture angle. And things that roll around on themselves are the best because they allow for all possible contact angle liquids on that red surface material. I'm going to talk more about the nature of this material and coatings that you can put on it. But part of the story, a big part of the story, is to recognize the texture side of it as well. So the physics as well as the chemistry. So let's look at some molecules. And this is pretty much what was known in the field when we started this work. And these sort of exotic molecules, silicone-like I mentioned, these are called silsesquioxanes, or SiO 1.5 is the stoichiometry of that. Not SiO like siloxanes, and not SiO2 like sand, but SiO 1.5. And our colleagues at the Air Force that we're collaborating with and who fund our research had been making these POS molecules with certain kinds of side groups, in particular side groups that contain a partially perfluorinated alkyl group. And we have found that on flat surfaces, these POS molecules, when spin-coated on a silicon wafer, give the highest known contact angles on a flat surface. And the question is why? When we leave this room, you won't have the answer. I'm hoping, Ed, you'll think about this and let me know. But this is the what. We'll get to the why. I'll make some speculative comments toward the end. So it's a little better than Teflon when water is the wetting fluid. Now, when, in this case, octane is the wetting fluid, first of all, you see a couple of things. Water spreads on Teflon. Octane spreads on Teflon, and the contact angle is only 40 degrees that you see there. But on this fluoropos, there's quite a significant enhancement of the non-wettable character owing to this particular molecule. And so how do you approach this problem? We're not going to do calculations. I told you I'm a molecule-oriented guy, not the math physics orientation. It's a kind of brute force structure property approach, and we're lucky to have the brutes out at the Air Force, Edwards Air Force Base, making this wonderful set of molecules for us. And I think you can see what we're doing here. These so-called T8 cages, the SiO 1.5 POS molecules. Then there's these Q where the silicon is connected to 4 oxygens, the rings and other rings, and then this linear molecule. So there's certain analog behavior in these things and various kinds of structural rigidity or mobility coming into play. And we can do other things like varying the fluoroalkyl group along the side, vary the length of that and the structure of it and so on. I'll just dance through a couple of examples and speculate on why this particular molecule with that particular side group is the best. You can characterize these molecules. This is a set. I'm sorry about the cutoff. It's not important. This is the fluorooctyl POS. We call it, that's the fluorooctyl, but we call it fluorodecyl POS with the fluoro group being 8 carbons long. It gives the lowest critical surface tension or solid surface energy. And the way we characterize these is to take a relatively narrow set of liquids, all alkanes, in a very narrow range, relatively narrow range of surface energy from about 15 up to 25 here, and simply make contact angle measurements as a function of the surface tension of the liquid and extrapolate them to 0 contact angle, or cosine theta equals 1. And Zisman, this is the classic Zisman analysis, and this critical contact angle is somehow a reflection of the solid surface energy, although even Zisman himself said it is not the solid surface energy. We felt that this extrapolation and the relatively narrow range of liquid contacting that you can do was inadequate. We felt that, for example, if we used other liquids beyond this very narrow range, that we were clearly finding other issues, other ways in which the probing liquid was interacting with the surface that was underneath it. And so we felt like a better way of analyzing this was available. And there's all smooth surfaces, yeah. And here it is. We went back to what's really the content of Ed's thesis, basic information on cohesive and adhesive, if you like, work of adhesion ideas. And I won't bother you with the details other than to say that other people in this period of time in the 1950s and early 1960s, Girifalco and Good, proposed a particular way of describing the work of adhesion. And that's shown here. And we make use of that equation combined with Young's equation to give a particular way in which the measured cosine of the contact angle should vary with the liquid surface tension. And the question is, do the data follow that? Do you get a reliable value of the solid surface energy? And can you learn anything beyond what you would get from the Zisman behavior? Well, first of all, the nice thing about this analysis, yes, the fit is better, and there's some sort of way of proving that this fit is better than the original Zisman plot, and that's pretty obvious anyway. But what's nice about this is if you look at this equation, when the cosine of theta is 0, in other words, when you're at 90-degree contact angle, then you have within your data set, not as an extrapolation, you have a point at which the solid surface energy is 1/4 of the value of the contacting liquid surface energy. So you don't have to extrapolate. And this is not really an extrapolation, that's just a continuation of the fit. And you can see in all of the results that the actual energy of the surface, gamma SV, solid surface energy, is always a little bit bigger than the Zisman extrapolation. Okay, so just running through this, the fluorodecylphos with 8 fluorinated carbons here, you need these two, as Ed and other good chemists will know. If you try to put those fluorinated groups right against the silicon, the bond is not stable, so you always bridge it with these 2 methylenes. But the fluorodecylphos is always the best, but the octyl and so on are okay until you start to make the chain too short, and then it becomes quite a bit higher in surface energy. We wanted to understand a little bit deeper what was going on at the molecular level. Is this because the underlying methylenes are starting to show, the oxygen group starting to be sensed by the probing liquid, or what are the reasons? And the answer to that lies here in the way in which Girifalco and Good showed that the non-dispersive part, or the polar part of the interaction of the liquid with the solid, could be broken up into, guess what, proton donating, hydrogen bond donating, hydrogen bond accepting groups, exactly the kind of thing we were talking, we heard spoken about before. And again, don't worry about the details of this equation. What it allows you to do is to pick 3 liquids that will allow you to pick out of the contact angle behavior the proton hydrogen bond donating, hydrogen bond accepting, and dispersive part of the interaction of that solid and the probing liquid. And here you see what's going on. What's going on is that if you simply look at the fit, you get a particular value for the solid surface energy, and we get a value of 9.3. If you use these three probing liquids and that long, messy equation that I showed you earlier, you find out that this fluorodecyl POS with the 8 fluorinated groups has dispersive solid surface energy component of 10 and a certain amount of gamma plus, that would be the hydrogen bond donating character, and a little bit more hydrogen bond accepting. This would be the hydrogen bond donating, hydrogen bond accepting character, and almost a fairly good agreement with the value of the solid surface energy that you get by simply fitting the data. And so we're using this technique to try to probe further into the understanding of how our molecules behave. But what's going on for the best molecule, this fluorodecyl POS, is that this number is low and these numbers are essentially zero. It doesn't engage in hydrogen bonding, and the dispersive part, which dominates the surface energy, is also numerically quite low. And what happens is when you start to fiddle with the nature of what's on the side, the dispersive character of the interactions gets larger. The hydrogen bonding part does grow, and I'll show you, I could show you some numbers where these get to be quite large with the linear molecules and so on. But this number also gets bigger for all of the other molecules besides the fluorodecyl POS. And what we think is happening is that the Teflon-like character, the CF2s, are actually interacting with the liquids in a way that's much stronger than the CF3s that are sitting on the surface. And so a kind of speculative summary of all the data that we have so far. I wouldn't call it a mechanism, just simply speculation that summarizes what we've seen. That cage molecule is relatively large. It's still a molecule. It's a nanometer or so across. But it does provide a kind of scaffold or a structure that allows these 10 carbon, 8 of which are fluorinated, to come to the surface and organize those CF3 groups in a way that's very favorable for non-wetting. That's point one. When the liquid probes that surface, the surface might like to rearrange. But the fact that that cage is so large, that's not going to be very likely. It's not going to be facilitated because of that large cage. When we have the rings and the linear molecules, that rearrangement is much more readily occurring, and we see both larger values of solid surface energy and bigger hysteresis in the advancing and receding nature of the contact angle. We think that that 10 carbon chain, again 8 of which are fluorinated, is just the right length, and there's been work in the past that the 8 carbon chain is really just about right for packing that will allow the CF3 groups to form at the surface in a more or less closed packed way. There are calculations that show that closed packed CF3 groups should give a solid surface energy around 6 or 7, and we're seeing 9 or 10. So I say the rings and linear molecules are too flexible. The flexibility disrupts the CF3 packing, and it allows these higher energy groups that are underneath to be seen or sensed by the probing liquid. Very much a sort of hypothesis. It would be interesting to be able to probe this comment in a little more quantitative way. Now, the fluorodecyl side chain, or that 8 carbon thing I've said is optimal, but it might not be optimal. If you plot up our data, everything that we've seen so far, the Zisman analysis or our Ghirafalco-Good analysis shows that as you change the length of the side chain or the number of perfluorinated carbons in the side chain, the solid surface energy decreases, and our best value is down here a little bit below 10. But it doesn't look like it's necessarily optimized itself yet. So we've convinced our friends at the Air Force to continue making the dodecyl and so on side chains on these POS molecules. We have large spirited arguments in my group. I'm convinced that if you keep increasing the length, it's going to go back up, because we know that Teflon is up here around 19. Everybody knows the surface energy of Teflon. It's 19. So I think there's a minimum. Others in my group, Dave said that students never follow instructions. They also never agree. But it doesn't matter. We're going to look into this if we can get the molecules out of our Air Force colleagues. So this is very much a work in progress. So to be continued. I just want to end with going back to what we're doing to use these molecules to reach our goal of making omniphobic surfaces. I have 2 or 3 slides left, and then we can all have lunch. Here is an omniphobic fabric. Octane, we can actually put pentane on this fabric, and it won't wet. I invite you, after lunch, get a little beaker, even methanol, and go around and put it on anything. It spreads. Octane spreads on everything, and you're seeing a drop. These dyes are just for your viewing pleasure. They don't affect the results, and when we do the real experiments, we don't have the dyes in there. But there it is, an omniphobic fabric, and the reason that octane can sit there is, first of all, this fabric is coated with this fluorodecyl POS. That's the chemistry side. But it also has a fabric texture, the topography of which is reentrant. So there's a weave side of this fabric, and there's a surface coating, if you like, side of this fabric that makes it work. We know that the relative spacing of the fibers and the spacing between them, R plus D over R, the radius of the fabrics plus the spacing between them divided by the radius, dimensionless number. If you increase that spacing, the stability of the drops becomes less, and the lowest surface tension liquid drops into the fabric. And as you keep stretching this fabric, you can sort of selectively titrate, if you like, the surface tension of the liquids. But it's really this that's interesting. And as soon as we published this paper, you can imagine we got funding from the Army. We're looking at military uniforms. This could be very useful as well as interesting and entertaining. And so we're looking at Army fabrics. We think that they need to reweave their fabric. They think that we just need to supply the optimal coating, and we're negotiating with them about the right way to go. I want to end with another couple of slides that are, I think, the simplest kind of experiments that I think Ed would appreciate. He used to come into the lab lectures of this class we taught together with a little shoebox, and he'd fiddle and what's in the box. Everybody's so curious about what was going to happen. Do some very interesting demonstration that always worked. I don't know how that happened. I have this on film, so I know this demonstration is going to work. But Ed, these are kind of simple experiments, and why do we do these experiments? Because we want to understand the pressure dependence. I showed you the spacing dependence of the fabric. But what if you wanted to push the fabric under water or under octane? How deep can you go before it would wet? The pressure dependence of this is actually really the most fundamental part of what we've done. And, oh dear, yeah. I want to show you this movie. We're looking not at fabrics here. They're effectively fabrics. They're screens, meshes. And it's an experiment you can intuitively understand. We're going to push it underneath the water, and we're going to see at what depth or what pressure the water wets into this fabric or mesh. And it will depend. It'll depend on the coating. It'll depend on the spacing, the size, and everything else of this mesh. I'm just going to show you 2 meshes that differ in spacing of the mesh at constant size. That shininess is where it's non-wetted, and there you can see this is wet, this one isn't yet. So very simple experiments like this allow us to quantify the depth or the pressure at which this structure breaks through and becomes wet, and this structure is down here somewhere lower. The details of that pressure dependence are contained here, and this is not the time to try to tell you what's in this equation. There's chemistry, there's relative spacing, and most importantly, those things can be varied over certain ranges. And the fluorodecyl POS molecule that I showed you allows us to optimize this piece of the equation. But it's here where the opportunities lie. The pressure that this will withstand, or the depth to which you can push this, goes like 1 over r. R is the size of these objects. So instead of having an 83 micron mesh at various relative spacings, that's what these numbers mean, if I had an 83 nanometer mesh, then these numbers would be 1,000 times bigger. You could push these things down tens of meters rather than some number of centimeters. So there's an opportunity for having very, very robust fabrics. That's what I said to the Army. Just weave your fabrics out of something much, much smaller. Easier said than done, they say. That's where the surface chemistry allows us to dial back. All right. I'm just going to end with something maybe not appropriate for a pre-lunch slide, but there are reasons why these, a few centimeters of depth might be interesting. In fact, a matter of life and death. Here's a little spider. By the way, this thing is called a plastron, this air trapped inside of some kind of structure. This little water spider, not so little in this picture, carries a plastron on its, thorax or carcass there, whatever you call it, and it swims around. And now the question is, how far underwater is it, and why is it doing this? You'll see in a minute that it's doing this to tend to some eggs. That's the part that interests me, the plastron. It goes up to the surface, renews it, and adds the air from the gap into this little dome that it's building. And we'll continue doing it and eventually bring the eggs inside and tend to them. But there's the depth. That depth is on the order of maybe 10 centimeters or less. So there's an example of nature making use of some kind of rough surface with a plastron and allowing this creature to develop a safe haven in order to tend to its eggs. That's where I want to stop. I'll end with things that I might have said at the beginning. This is definitely a collaborative piece of work. We've had a lot of good luck with our collaborations and our students. That's Joe Mabry. He's the guy that made these POS molecules, the fluorodecyl POS, and all the other molecules that are allowing us to look at the chemistry side. A lot of the physics, this pressure dependence and so on, has been worked out by Gareth McKinley and 2 mechanical engineering graduate students. Gareth, of course, Ed, you had him in 1068. He was in the first class of PPST that derived directly from that paper that we wrote, and of course the name PPST was yours. You invented the terminology. So that's Gareth McKinley, Joe Mabry. Anish Tuteja was a postdoc in this project. He's now at the University of Michigan on the faculty. Jesus Guardado has done some of the measurements. He's an undergraduate in the material science department. But the star of the show really is Shri. A lot of those data, all of the work on these interesting molecules is being carried by Srirang Chatra, who is a PhD CEP student in the department, and really the mover and the shaker in this piece of the project. And Ed, one more person here. This is Adam Moyler, who is a grandchild of mine. Talk about academic trees. You taught his thesis advisor, Frank Bates, polymer physical chemistry, and he's now hanging around in the hallways of Building 66. And I'll just end with one other thing. I mentioned all of my appreciations early on. I miss you, Ed. You used to come into that little emeritus office next to mine, putter around with your mail and tinker with a few. I never knew quite what you're doing in there. That office, and you generously gave it up for Brad Olson, who's sitting behind you, a new assistant professor who's doing polymer work, teaching polymer synthesis and other things. My office is too big as it is. And I think the key to that old office, if you kept it, definitely opens the door to my office. So just come on in. We can sit down and enjoy each other's company and talk about all of these things in detail. And I'll just end again by saying I owe you a lot, Ed, and thank you very much.
Any last-minute questions? You want to know when you can buy a shirt that has those properties?
A necktie.
Obviously, it's hugely important with regard to the wedding as it relates to textiles and uniforms, etc. But you also have shown here, have you considered using these devices, these materials, as a separation barrier? Of course you have.
You're a smart guy,
Okay.
Sam. We have, through the MIT Energy Initiative, we have a couple of projects.
Yeah.
One is to do exactly what you say, undersea separation of oil and water so that you don't have to bring it all up to the surface to get this brine cleaned out. You can do it below. The pressure dependence is very important. So there we have to beat this problem of a few centimeters and get into the few tens or hundreds of meters. That won't be easy. But let me just finish. The second thing we're working on is very timely. We're a little late, but we're also working, and that's what Adam is working on, the adhesion of solid phases to these kinds of textured surfaces, namely ice for wings of airplanes, and also hydrates or clathrates that form, and we've been reading about that in the news. This dome gunked up with those clathrates, and we are working on that problem, but we haven't solved it. But we're thinking about our surfaces in that context.
Potentially hugely source of methane, as you already appreciate. Methane hydrates.
Yes.
But I was coming back to, say, surface temperatures, say, atmospheric pressure. How about the treatment of these materials to use separation of xylene isomers or separation of hydrocarbons just as barriers,
Yeah.
either as adsorbents?
It's amazing to hear you
Or-
inventing things that people are doing.
Oh,
That's to your great credit. I'm not
I
say that in admiration. Francesco Stolacci in our materials science department has materials like ours with the right kind of, he treats them with silicones. I think if he treated them with siloxanes, it might even be better. But through wicking or competitive wetting, he can separate toluene from xylene, for example. People are
Well,
hungry,
I
Sam.
think in the interest of the time, maybe you should ask your question to Bob over lunch.
Yeah, I'll sit with
I
him.
think a lot of people are probably about now interested in lunch. And so lunch, thank you very much, Bob.
You're welcome.